So in the class, in that I just considered a phase shift oscillator. So you can see the oscillators. I just explained all these things. So I just explained. So in the previous class, I was just considering about started with phase shift oscillator. In that phase shift oscillator, so anything. So before that, we have studied about the amplifier. So what are the characteristic parameters? What are the biasing problems? Everything we have discussed, and small signal equivalent circuit model. Also, we have developed high frequency equivalent circuit model, frequency response of an amplifier. So entire thing we have studied about the amplifier, and now it is the time for the to switch on to the applications of the amplifier along with the amplifier. So in one of the case, so we are going to start with the RC phase shift or FET based RC phase shift oscillator. So in the RC FET based RC phase shift oscillator, so you can see there is a this is a circuit diagram of an FET based RC phase shift oscillator, in which we are going to use this FET as an amplifier, and this RC network, so which has been developed. So we are going to take it as a feedback network. So this will be considered as a feedback network. So in any type of a circuit oscillators, we are going to have one amplifier and followed by one feedback network will be there. So amplifier is going to provide an gain. So it is going to provide an amplifier. The signal will be the input signal will be amplified, and the same thing, the output will be fed back to the input of the amplifier through the feedback network. So this feedback network, which is comprises of R and C section, which is nothing but RC feedback network. So here you can see three RC section which has been connected in the feedback between the output and the input. So here you can see the input is connected between gate and source, and the output of the final output of the feedback network, that is the voltage across the R, that is the feedback voltage that is being connected back to the input. So in this way, this is nothing but feedback network as well as the amplifier network. So here you can use any type of amplifier, whether it can be BJT or it can be FET, and through the power supply VDD. So once you turn on the power supply, so it will start providing oscillation. So we have seen that what is the necessary condition that has to be satisfied in order to oscillate. So that is nothing but circuit to function as an oscillator. So you should have Parkinson's criteria. So based upon that Parkinson criteria only, so you're going to see some circuits getting oscillation. So oscillations. So in order to get an oscillation for sustained oscillation, so you should say that it has to satisfy the total phase shift around the loop must be equal to 0. And then so you have, along with that, so you should have a loop gain, it should be equal to 1 or greater than 1. So in that case, the circuit is going to oscillate. So here is given a circuit, and also one more thing is that so whatever we are going to use in this RC phase shift RC network, which is used as a feedback network for which is used for a feedback network for this which is used as a free feedback network for this circuit. So you can see this feedback network. So this using the passive component like R and C component which you are going to use, then you can get the frequency of oscillation will be less than 100 kilohertz. So you will be having oscillation, so as well as the oscillation frequency, so it will be not greater than 100 kilohertz, less than 100 kilohertz. That means it will be whatever the phase shift oscillator you are going to use, that will be operating only for low frequency of operation. Okay, so less than 100 kilowatts. So the feedback network which you are going to use, so it is nothing but RC phase shift network. So RC can have C and R combination in the feedback network. So we also know that C, since there is the presence of reactance component, so it is also dependent upon the frequency. So frequency, so when the output of the amplifier, so since it is a common source amplifier with the source resistance in series has been connected, so this type of amplifier is going to provide an internal phase shift of 180 degrees. So the because of the configuration of the circuit itself, the transistor, so FET is going to provide an 180 degree phase shift between the input and output. If you see, So you will be getting 180-degree phase shift. Output will be 180-degree out of phase. So because of that, we have already examined by deriving the components. So that is the gain expression when we have derived. So it was having minus gm into rd parallel rl. So divided by 1 plus gm into rs for the common source with source resistance. For that is for open circuit voltage gain, or it will you can call it as a open circuit voltage gain. So in that case, you can see the gain will be having minus symbol, so that minus symbol indicates that so the output was 180-degree out of phase with respect to input. So this is going to provide 180-degree phase shift. Another thing is that so the feedback network, so the total phase shift around the loop. So this is just like a loop. You can see if you are going to start from here, so output again it come back to the output. If you see, so that is nothing but a looping. So in this feedback network is nothing but from the output we are going to give input to this feedback network, and followed by that output of the feedback network to be again fed back to the input side. So that's the this completes the looping condition for this circuit. So in order to get a total overall phase shift, so this feedback network should also give a total phase shift of 180 degree. If it is going to provide, then you have according to from the network theory. So we have seen that. So whenever it is going to be passed any signal, so with C and R section or R and C section, if you are going to pass, it is going to provide a 60-degree phase shift. So here you are going to have a 3 R and C section. So since you are going to have a 3 R and C section, so each will be having the 60-degree phase shift. So because of that, from the input to the feedback network to the output of the feedback network, if you just imagine, so if you just see the output, so the output will be 180-degree out of phase. So because of this feedback network, okay. Um, and because of this feedback network, it is going to provide additional 180-degree phase shift. So either you can use C and R type of network configuration, or R and C type of configuration. So each will be providing 180-degree phase shift. So when you are using the C and R configuration, then it is going to be considered as the phase lead network, and it is going to have a advanced plus 60-degree phase shift will be there. Whereas if you are going to use R and C, then you will be having the minus 60-degree phase shift will be there. So because of that, you can say that so whatever the combination if you are going to use, either it is going to provide a plus 180-degree phase shift or minus 180-degree phase shift. Suppose here you will be getting the output is equal to minus gm into r dash, so it is going to have a phase lag network. Suppose if it is going to have a 180-degree negative, so that means it is going to have a phase shift of 180-degree means when compared to input. So it is going to provide a plus 180 using this configuration. So plus 180 plus 180, it is going to provide a 360-degree, that is equal to 0-degree phase shift, or else a plus 180-degree and minus 180-degree also, it is going to provide a phase shift of 0-degree. So in that case, we are going to consider this as a total phase shift around the loop is equal to 0-degree. So since we are going to have a total phase shift of the 0-degree, so this is going to satisfy the first Parkinson criteria of oscillation. So second condition, it is required that the loop gain should be equal to 1. So the loop gain is nothing but what? So the gain is here you are going to have an amplifier gain, along with the amplifier gain, so you are going to also have a feedback gain. And if you look at the amplifier network, so it will be comprising of transistors. So, transistor between the input and output, if you see, so there is a huge amount of amplitude increase in the output voltage when compared to that of input voltage. So this is because of the transistor, which is going to be operating as an amplifier. Whereas in this in the feedback network, if you consider, so you are not going to have any amplifier over here. So that means you are not having any BJT or FET in the feedback network. So it is comprising of only a passive component. So it is comprising of only R and C section. So it is not going to have any active network, and it is not going to have, it is going to have only the passive components. So passive components means you know that it is going to consume of the it is going to consume the signal. So whether it can be voltage or current signal, it is going to reduce the power dissipation, and hence it is going to increase the power dissipation, and hence the amplitude of the signal will be still it is going to reduce. So because of this passive components present in the feedback part, if you consider the output of the feedback network with respect to input, not only the phase shift will be 180-degree, along with that the amplitude will also going to be get reduced. So the amplitude of the output, that means output voltage amplitude whatever it will be there, so that voltage is going to be getting reduced as it passes through each of the RNC section. So along with the phase shift, you are going to have so phase amplitude reduction also you are going to have. So amplitude reduction means what? There will be reduction in the gain. So when compared to the output feedback with respect to output of the amplifier, so you can see there is the amplifier reduction will take place. So because of this passive component, and we are going to see how much reduction it is going to happen. And for that to take, so we need to first reduce the circuit with its corresponding AC equivalent circuit. So this is our AC equivalent circuit which is going to be written, followed by the RC phase shift network it has been written. So here the input voltage will be applied between the gate and source. So you are going to have input voltage denoted as VI, and for that input is going to control the output current between the drain and source. So for that you are going to have a control current source which is going to be nothing but a voltage is going to control the current. So it is given by GM times of VI. And we can see this is the two resistance, that is a drain resistance along with the finite output resistance RD have been connected in parallel. So it will be in the parallel combination. So because of that, equivalent resistance RD dash will be equal to nearly equal to that value of the RD drain resistance itself, because the drain resistance is very small when compared to the finite output resistance. So small RD. So you're going to have an equivalent if these two are connected, if these two are being in parallel combination means correspondingly. So you're going to have a equivalent resistance RD dash. It is going to have to the smaller value, which is nothing but RD. So it is going to have a RD as a equivalent resistance, and followed by this RC and R. So we also know that the resistance which is going to be used or which is going to be used in the feedback network resistance will be usually very much greater than this equivalent RD dash, and hence it is not going to provide any effect on the output characteristics. And also we can see this is about the feedback voltage. So if you can see the feedback voltage which is nothing but the voltage across the resistance R will be fed back to the input to the gate again. So that is nothing but the feedback voltage. So feedback voltage will be developed across the last section of the resistance R, which is going to connect to the gate of the FET. So you can just simplify that circuit with equivalent model. So it is here in this you are going to have, instead of current source connected in parallel, so you can write it in the equivalent link. So the circuit of this entire thing, so here you can see the circuit can be replaced with the voltage source along with the series resistance connected between the voltage source. So this is what you are going to replace this entire thing. So GM into VI is the current source, and the RT dash is the equivalent resistance. Since these two are being connected in parallel, so I can write this entire thing into voltage source connected in series with that. So the same thing it is going to hold. So you are going to write it as a voltage source connected in series with the resistance, and because of that you can see this as a voltage across this node will be equal to V naught. Okay. And you can see the simplifications, and you can see what is the current that is flowing in the first section denoted as I1, second is I2, and third is IT. And we can easily find out the current expressions and the voltage by applying KVL in each of the R and C section, and you can see this is the value of the current. So I1 will be the, in the first section only I1 will be the current will be flowing, and opposite to that I2 will be flowing in the first KVL rule. So when you are applying to this one, so you are having I1 is a current and I2 is flowing opposite to that. So I am going to write it as a minus I2, and it will be equal to that of the voltage, which is nothing but Gm into RD dash into Vi. So that is what the voltage. And similarly second loop equation, third loop equation you are going to write. And also we know that the feedback voltage which is fed back to the input to the gate of the FET will be equal to the current, that is feedback voltage Vf, which is nothing but I3 into R. So that is nothing but so this is nothing but a voltage, that is a feedback voltage which is nothing but I3 into R. And now we need to find out the loop gain. So loop gain, so I'm going to write it as a loop gain as A into beta. So A into beta, so in which we can see the feedback voltage will be equal to what? So this feedback voltage to the that is nothing but a gain, loop gain. So loop gain is A into beta is nothing but so how much is the gain? So which you are going to get. So output is what? So output is output is Vf and input is Vi. So with respect to output to input, if I am going to find out, then I can easily find out the loop gain as equal to A into beta. So in order to find out the Vf, so I can write Vf is equal to I3 into R. So if I substitute the value of I3, so you can easily find out the, so it will be equal to A into beta. So A is nothing but minus Gm into RD dash, whereas beta is nothing but the feedback gain. So which can be written in terms of since it is going to have only R and C component which is present over here, and if you substitute and if you solve this equation, three equations, you are going to get them. You are going to get the expression. So that expression it is going to have 1 minus 5 alpha square plus j into alpha cube minus 6 alpha. So this is the network. So when you simplify, so these three voltage equations if you are going to substitute, then you can easily find out the values of for expression. So which is going to have a real part as well as the imaginary part. So whenever you're going to have an imaginary part, so that if you're going to substitute which is, all the loop gain will be not having imaginary, so it will be having only a real part. So the imaginary part expression is going to substitute as equal to 0. So alpha is nothing but 1 by omega RC. So here I just written with another coefficient alpha, which is nothing but 1 by omega RC. So this value if I substitute, the equation is going to hold the same as the expression. So in place of 1 by omega RC, I am just replacing it with the constant alpha. And here the imaginary term I am going to equate to 0, and hence I am going to find out the frequency of oscillation. So how much the frequency is going to get oscillated, that the frequency of oscillation is going to be determined by using this equation. So if I substitute or if I simplify this equation, I will be getting the frequency of oscillation of this circuit. So the frequency of oscillation is given by 1 by 2 pi RC into square root of 6. So this square root of 6 can also be written like 2 into 3. So 3 corresponds to the number of R and C sections. So 2 into 3 or 2n. So I can simplify this expression frequency of oscillation for a FET based phase shift oscillator as 1 by 2 pi RC into square root of 2n. So 2n, n corresponds to number of RC that has been connected in the feedback network. So 3 RC section is has been there. So I'm going to write 2 into 3, that will be equal to 6. So this gives the frequency of oscillation for the given circuit. And now we need to find out the gain. So along with the frequency of oscillation, so we will be getting the gain. So gain, if I am going to substitute the value, so the gain will be what we will call, so omega RC, right? So alpha is equal to 1 by omega RC. Okay, then if I substitute the value, so here if I substitute the value of the gain reduction, so you'll be getting the gain from the output feedback to the input terminal. So uh, if I'm going to have the output and input, so when I see I will be getting the gain expression, as this is the GM into RD dash is the output gain expression of an amplifier. And if I see the gain reduction, so if I see the output voltage to here to feedback voltage, if I see the feedback voltage amplitude is going to be reduced, and it will be reduced by a factor of around approximately equal to 29. So 29 will be the value. So that is gain reduction. So that means the output amplitude of the feedback signal when compared to the output of the amplifier signal, if I compare, so the amplitude has been reduced by a factor of 29. So this 29 indicates what? So this is nothing but gain of the feedback network. So gain of the feedback network is what? So 1 over 29. So whatever the output amplifier output is there, so from here whatever the output voltage you are going to get over here, so that means here the amplifier is going to have a gain of what? Minus gm into RD dash. So this output will be getting reduced in amplitude when it comes over here. So that is how much it has been reduced. It has been reduced by a factor of 29. So this 29 so is a reduction gain reduction factor of the feedback network. So this feedback network is going to have how much the gain? The gain is going to have 1 over 29. So that is nothing but because it is not having any active component like transistors or BJT or FET, if it is not there inside the feedback network. So whatever you send the signal, the signal amplitude is going to be reduced over here. So how much it has reduced? It has reduced around 29. So the what is the gain for this feedback network? So it is having a reduction in the gain. So that is reduction in the gain is how much? 1 over 29. So that 1 over 29 is the gain. So if I want to find out the loop gain means, so this will be the loop gain. So this is going to have an amplifier as amplifier is going to have a gain of what? So gm into RD dash, and beta is nothing but the gain of this one. It is going to have 1 over 29. So it is nothing but gm into RD dash by 29. So this loop gain should be equal to 1. So whenever it is going to equal to 1, that means loop gain um, whenever the loop gain is equal to 1, or if it is greater than 1, then only the circuit is going to oscillate. So for that reason we are going to find out what is the loop. So loop gain. So the loop gain, in order to make the loop gain should be equal to 1, so I should have the transistor amplifier gain should be greater than 29. So if the amplifier gain, so gm into RD dash, if it is greater than 29, then the loop gain is going to be equal to 1. So Gm into RD dash must be equal to or greater than 29. So here it should be greater than 29. If it is greater than 29, then it is going to have a loop gain will be greater than 1. That means it will be equal to 1 or it will be greater than 1. So if it is greater than 1, so it is going to satisfy both the loop gain as well as the phase shift around the loop. So both it has been satisfied according to the Parkinson criteria. So the circuit will start oscillating. So in that case only the circuit is going to oscillate with a sustained oscillation without any triggering input signal. It will just start oscillating by its own signal. So it is going to oscillate by its own. So that is what the Gm into RD dash. So it should be greater than 29. So the amplifier gain should be greater than Gm into RD dash. So the amplifier gain should be greater than 29, and beta is the feedback network. So this feedback network is going to have a reduction of voltage of 1 over 29. So this indicates that in order to have a loop gain, so amplifier gain must be greater than 29. Then only you are going to have a loop gain which will be equal to 1. So if it is a Gm into RD dash, if it is equal to 29 means 29 divided by 29, so it will be equal to 1. So if it is equal to 1, then it is going to satisfy Parkinson criteria of loop gain to be equal to 1, and also it is going to have a phase shift around the loop to be equal to 0 degrees. So it is going to circuit will get oscillated. So this is about the RC phase shift oscillator. So next, moving on to the next topic, which is nothing but LC and crystal oscillator. So after studying about the RC phase shift oscillator, so we are going to study about the next type of classification of the oscillator. So the type of the feedback which you are going to give. So if you are going to have LC corresponds to what? So L and C corresponds to inductor as well as a capacitor. So L and C, if it is present along with the BJT or FET, if you are going to have a feedback element comprising of L and C component, so obviously you are going to have a obviously that type of oscillators will be called as LC tuned oscillators, and it will be having a L and C. So it is also called as a tank circuit you will be calling. So why you are going to call it as a tank circuit? Because since you are going to have the feedback element, so feedback network comprising of capacitor and inductor. So if you are going to have a capacitor or inductor, so you can see in both of the circuits, you are going to have either capacitor and feedback. So in this entire thing, it is going to act like a feedback for both circuits. If you can see, so it is going to act as a feedback network. So in the feedback network, if you are going to have L and C, then you are going to call it as a that is nothing but uh, tank circuit. So you're going to call it as a tank circuit. So the classification of LC has been further done. So based upon the type of based upon how the inductor and capacitor has been connected. So if you are going to have a feedback network comprising of three impedance. Suppose normally, so LC oscillators and all, you are going to have a three impedance or three impedance parameter will be there. So Z1, Z2, and Z3. So normally Z1 and Z2 will be made up of same element. So here also you can see Z1, Z2, and Z3 as a inductor. So Z1 and Z2 will be made up of same component. Here also you can see Z1 and Z2, it is made up of inductor over here, and whereas here it is made up of same capacitors. So C1 and C2. And the third impedance Z3 will be normally the opposite type. So that is if it is a capacitor in there, so then um, next will be the inductor. Sorry, so mute yourself. All of you mute yourself. So I'll just take 5 minutes of time. So if you are going to have a feedback element, so comprising in this fashion, if you are going to have two capacitors and one inductor, it is there, then that type of oscillators would be called as a Colpit oscillator. So you're going to have a Colpit oscillator as well as Hartley oscillator. So here we'll just look at the circuit diagram. The circuit diagram remains same. So you'll be having one amplifier network, it should be there. So the amplifier network can be either BJT or it can be FET or it can be any operational amplifier. So any amplifier, so it can be having a term between the input and output. So amplifier can be of BJT type or a FET type, or it can be any operational amplifier. And then so feedback network should be of capacitor and inductor. So if it is a capacitor and inductors are there, then it is called as a then it will be called as a LC oscillator, or it is also called as a tank circuit. So feedback elements, either if it is having, so it can be consisting of two types. One is two capacitors with one inductor, or two inductors with one capacitor. So if we are going to have two capacitor dividers, and one inductor is there, so if that is a feedback element means, then you will going to call it as a Colpit. So easy to remember. So if Colpit means, you should remember C. Colpit stands for C. So C stands for capacitor. So two capacitors you have to remember. So two capacitors will be there, and one inductor. So Hartley or Colpit oscillator, you will be having both inductor as well as capacitors will be there. And easy to remember means, Colpit means two capacitors will be there. You have to recall, because C stands for capacitor anta ನೆನ್ಪಿಟ್ಕೊಳ್ರಿ. Colpit means, C stands for capacitor. So two capacitors will be there. And Hartley means, you should remember the SI unit. So unit of inductor is what? Henry. So you should remember that you should have inductor means, you're going to have what? Inductor means Henry. So Henry stands for inductor. So you'll be having two inductors and one capacitor will be there in the feedback path. So if it is there, so then you can call it as a Colpit Hartley as well as a Colpit oscillator. This is nothing but Hartley in the feedback element, and this will be considered as the Colpit oscillator. So along with that, we are going to have another one. Resistance has been connected between the collector to emitter. So between the collector to emitter, or collector to ground, so you're going to have some resistance will be there. So this resistance is usually used, or it will be always connected. It will be always connected in order to overcome the losses that is going to happen between the inductor or capacitor. So inductor only some certain losses will be there. So because of charging losses will be there. Along with that, capacitor is also having some leakage current will be there. So in order to overcome that, so in order to provide certain, in order to overcome the losses, so you're going to connect the resistance R between the collector to emitter. Here also you're going to have a connected one resistance which is going to provide a between the collector and emitter. So normally, so this is nothing but amplifier network. So it is nothing but amplifier network, and this is nothing but a feedback network. So feedback network from the output of the collector, and it has been given to the input of to the base. So that is nothing but a feedback network. So one is Colpit oscillator, another one is Hartley oscillator. So normally, why this? If you are going to use this type of LC tank circuit, you are going to use, then this type of circuit is going to be providing an oscillation frequency greater than 10 kilohertz. So what was the drawback in the RC phase shift oscillator? It was limited only up to 100 of kilohertz. But if you are going for LC as well as crystal oscillators in the feedback path, so usually crystal oscillators also you will be having the electrical equivalent. If you are going to write the crystal oscillator, then you are going to have R, L, and C. So it is going to be there. So when you are going to have inductor and capacitor in the feedback part, so normally you are going to have a frequency of operation will be very high. So that is what you are going to see. So 100 kilohertz to few hundreds of megahertz, you are going to get the oscillation frequency. So because of that, you are going to have a oscillation, the crystal LC type of oscillator to be operated at a higher frequency range of operation. At the same time, so we are going to see that the value of the Q, the quality factor. So in any type of oscillators, we are going to have a um, in any type of oscillators, you are going to have a feedback. If it is a LNC circuit is there, so you are going to have a high Q factor. So high Q factor is the quality factor for oscillators. So high Q factor means is going to provide an oscillations at a very high frequency, as well as whenever the quality Q factor is high, then that type of oscillator is going to provide a more stable oscillations when compared to the other lower Q. So if you are going to consider the RC phase shift oscillator, the value of the Q factor will be very less when compared to the Q factor of the LC tuned circuit. And another thing is that, so we are going to call, whenever you are going to have a feedback path comprising of inductor and capacitor. So this will be called, also called as a tank circuit. So why we are going to call it as a tank circuit? So because it is an energy reservoir. So it is nothing but it is going to have a storage element. So it is called as energy storage device, because we know that capacitor as well as inductor. So for what purpose they are going to use? So it is going to use for, so it is going to use for what? So it is going to store the charge. So capacitor is also going to store the charge, and the inductor, whereas it is going to store the electrostatic charge, whereas inductor is going to store the electrostatic charge, as well as here it will be magnetic magnetic charge it is going to store. So whenever these two components have been kept in the feedback path, so you're going to have a energy storage. So if it is going to have some voltage is there across this terminal means, so it is going to charge the polarity of the capacitor. Suppose consider only one capacitor and one inductor is there, so it is going to have what? So it is going to store the charge. So whenever you give the voltage across here, it starts charging the capacitor. The current is going to charge the capacitor C1 to its peak charging voltage, and in the direction plus and minus. Suppose if it is in the direction of the current means, it is going to have plus charge to be across this top plate and the negative charge to be developed across the bottom plate. And in that case, we are going to have plus and minus charge to be developed across this capacitor. So when an inductor has been connected in parallel to this capacitor means, so the normally, so whatever charge is there, it is going to discharge towards the resistance as well as inductor path. So it is going to, so causes the current to flow, the electrons or holes. It is going to cause to move, and it is going to move, and it is going to be move towards the inductor part. So whenever it is inductor is there, so whenever the current or the charges will start moving in this inductor, so it is going to develop a magnetic field. So because of the applied magnetic field, so because of this electro field, so it is going to develop magnetic. It is going to develop when electrons are flowing over here, so it is going to develop a current. So that is nothing but a back EMF. It is going to develop, and because of this back EMF, so the inductor is going to alter the and make the capacitor to discharge and regain the charge in the opposite way. So because of it is going to discharge whenever the capacitor is going to discharge completely through towards the inductor. Again, this inductor is going to recharge the capacitor in the reverse fashion because of the back EMF current. So because of that, the now the polarity of the capacitor is going to reverse, and it is going to be minus and plus it is going to have, and again it will start discharging towards here. So it is also going to discharge and it is also going to discharge, so that both will be maintaining as a energy reservoir. So because of that, you are going to see this as a tank circuit. So summary shows the figures of the two LC tuned oscillators. One is the Colpit configuration and another one is the Hartley configuration. So both you are using in a parallel fashion, and it is being connected between the collector and base. So between the collector and base, it is being connected. So and we can see we can see the fraction of the tuned circuit voltage will be, the fraction of this voltage will be given as an input to the feedback to the base of the terminal, so which is an input of feedback voltage. So this feedback is achieved when the capacitor divider in the case of capacitor divider in the case of Colpit oscillator, and inductor divider in the case of Hartley oscillator. So this is nothing but feedback voltage that is going to be applied to the transistor. So capacitor divider in the case of Colpit, and inductor divider in the case of Hartley oscillator. And we can say that oscillator we are going to have, along with that component, we are going to have a resistance R. So R is used to model the combination of the losses of the inductors and the load resistance of the oscillator. So whatever the inductor is going to have, practical inductors and the capacitors are going to have a leakage loss. So that loss will be overcome. In order to model that, so we are going to use a resistance R is going to model, and it will be connected between the collector to emitter. And then the frequency of oscillation of this is sufficiently frequency of operation. Suppose if the frequency of operation is sufficiently low, so what will happen? Suppose if I am going to use the frequency of the operation signal is very low, so at the low frequency the capacitive reactance will be inversely proportional to, so that it will be acting like an open circuit, and it will be feedback. So capacitor will be acting as an open circuit, and the entire thing it is going to be fed back through the inductor itself. So it is not going to be operated at low frequency, and the frequency of oscillation of the circuit will be determined by the resonance frequency. So when you are going to use LC oscillator as well as the crystal oscillator, you are going to operate or you are going to get the maximum frequency of oscillation only at particular frequency, so that whenever the frequency the circuit is oscillate, so that particular frequency in which you will be getting a maximum amplitude is called as a resonance frequency. So in that particular frequency, so it will be whenever the energy is maximum, so you will be having to operate at a particular frequency. That particular frequency is called as a resonance frequency. So if we see the frequency of oscillation for the Colpit oscillator and Hartley oscillator, so similar to how we have obtained for the RC phase shift oscillator, which is nothing but 1 by 2 pi RC into square root of 2n. In the case of RC phase shift network, so similarly, if you are going to find out the oscillator frequency, it will be equal to 1 by square root of L into C, 2 pi into square root of L into C. So 1 by 2 pi into square root of LC. So the way the inductor and capacitor has been connected in the Colpit as well as the Hartley, it has been given over here. So 1 by square root of, for the Colpit oscillator, it is given as 1 by square root of L into C1 C2 divided by C1 plus C2. So this is about the oscillation frequency for the Colpit, and for Hartley oscillator, it is 1 by square root of 2 pi into square root of 1 by 2 pi into square root of L1 plus L2 into C. So this is how the frequency of oscillation for the Hartley, and this is the frequency of oscillation for the Colpit oscillator. So with this, I will just conclude today's class session. So if you have any doubts, you can ask in tomorrow. So I'll just again I have to go the derivation part of this one. So if I'm going to derive this one, so you'll come to know about the loop gain and all. So in this, how the circuit will be transistor circuit, that is a Colpit oscillators, you're going to write it in detail, and you're going to write the corresponding expression, and you're going to find out the value of the resistance as well as capacitance, and you're going to find out the loop gain. So whenever it is going to satisfy, then only the circuit is going to, Hartley or Colpit is going to work like an oscillator. Okay, so I just conclude. I will just leave you the class at this time. So all of you must attend. So without fail. So it is compulsory. You need to attend in the next 10 minutes. So because the 310, 4th A and 320 onwards, 4th B is there. So that means within 10 minutes you should be available in that corresponding link. So for that reason, I'm just concluding the class now. Okay, so 5 minutes before I'm just concluding. Okay, bye.